Hello, welcome. Today let's try to solve Leetcode problem 505, the maze 2. So if you want to solve this problem, I suggest you solve the maze 1 first because that is the base of this problem. Yeah. So this is actually the code from the maze 1. So I'm gonna change a little bit of the maze 1 and then adapt it to maze 2. Although the maze 2 is a little bit harder than maze 1, but we can use the existing code of maze 1 to solve it. Yeah. If you understand the question of the maze 1, you will understand the maze 2 because the only difference is for maze 2, you just need to return the shortest distance. So basically, it is a Dijkstra's algorithm. For maze 1, so this is actually the code for maze 1. Yeah, you can check the videos I posted in YouTube for maze 1. If you understand that question, basically you can understand the maze 2 because there's only a little bit of change. Yeah. So here the maze 1 structure is a check function. This check function is just to check the positions of the ball. If it moved to the next position, it can be up, down, left, and right. And for here, this is just a basic BFS. Yeah. But for maze 2, we need to change this code and adapt it to the Dijkstra's algorithm. Yeah, now let me just change a little bit of this code and try to solve it. For the Dijkstra's algorithm, basically for this check function, we need to also check the distance because we want to return the shortest distance. Yeah. And the rules of the balls, how it moves, it will be according to the rules from the maze 1. It can go up, down, left, and right, but it must go to a destination. It cannot stay here. It must go down until here. Yeah, for the ball, it can go here, here, but it cannot stay just in the middle. It have to go to the ends. Yeah. Now let me just change it to the Dijkstra's algorithm. So for the Q, we're gonna use a PQ. So inside the PQ, it's gonna be a tuple. So the first one inside the PQ, it's gonna have a distance, and then I'm gonna have the x and y position. Basically, my starting point it is a start 0 and start 1. So this is the priority queue. Now I don't need to have the weighted set because that's just algorithm. For one way, you can use a weighted set, but another way is a distance array because that is much faster than the weighted set. So for here, I'm gonna prepare a distance array. So it's gonna be infinite times r times c. Yeah, let me change it to c. I don't know why I cannot type the capital C. Yeah, so this is the distance array. So for the beginning, the distance, yeah, the starting point. So where am I? I'm at this point. So how to calculate it? Yeah, basically you just need to turn this 2D array to a 1D array. So how you should do that? So you can use start with a 0, so it is those times c, it is the column, and plus start 1. So this is the distance. Yeah, this is just to turn this 2D array to 1D array. For example, this is a 2D array here, and for this point, it will be moved to here, next to this ball. Yeah, and for the next row, we just put it connected to a 1D array. Yeah, so for here, the distance array just use the start 0 times c plus start 1. So this is exactly, yeah, we compressed the 2D array to a 1D array. Yeah, normally we're gonna use this way as the distance array. Now the directions would be the same. For here, I'm gonna use a PQ because it is a priority queue, and I need to pop out. Yeah, so here I have the priority queue, so it would be hip hop, and inside it would be PQ, and also I need to have a distance. So this D is the distance. R and C are just the positions for this ball. Now I'm going to check it. If R equal to the destination, yeah, you can see here the destination is also an array with two indices. So we're gonna use the distance 0 and destination 0 and destination 1. So if this r equal to 0 and c equal to 1, we're gonna return the distance. Yeah, we're gonna just return this d. Now we're gonna here would be the same. We just check the directions and the row and column would be equal to the tag. I will change the tag function later, but here just imagine if I can calculate the distance. So for here, I'm gonna use a distance. Yeah, let me use a distance. Yeah, so for here, if I can calculate the distance, this is a row and column. Yeah, I'm gonna update the new distance. So here, this distance, I'm gonna use a cost. So this cost would be d plus the distance. So this is basically the Dijkstra's algorithm. It is not. It is a. Yeah. There's no difference. It is just a Dijkstra's algorithm. So now I don't need to check the weighted set. Yeah, because Dijkstra is also the BFS. This is why I can directly change this BFS to the Dijkstra's algorithm. Yeah. So if the cost is smaller than the distance array, so inside of the distance array, it's gonna be let me check. It's gonna be rho times c plus the column because this is the position. Yeah, as you can see, it is exactly like the starting point. The structure is totally the same, just to a 2D array to a 1D array for this distance array. If it is smaller, so we're gonna update this distance array. Yeah, we just cover this listed set because we're gonna not use it. Yeah, so the distance array would be equal to the cost, and here we just need to use a heap push. We just need to put the tuple inside the PQ, and the tuple, the first position would be a cost. Actually, this is the distance to my current point, and now I have a row and column, my current position. So basically, this is the entire code for the Dijkstra's algorithm. If I didn't find a shortest path, I just needed to return a -1. Yeah, so this is a -1. But up to now, I didn't finish the check function. As you know, I added some distance to this check function. It means I needed to calculate the distance. Yeah, if you if you didn't understand why I'm gonna do that, maybe you're gonna check the maze 1 for my video, and at the same time you're gonna understand the maze 2 easily. Now I'm gonna add a distance I'm gonna add a distance to this return for this tag. This tag is basically the same in maze 1. So for here, I just needed to add a distance. So d should plus equal to 1, and d will be start from 0. Yeah, because before I just needed to check the positions. Now I have to check the distance. So for each of the while loop, if it's inside the boundary and maze not equal to 1, the ball will, for example, it will go down until go to the wall, go to this position. And my distance will also be updated. Yeah, but until it goes to the wall, the distance will also updated. This means my final result, the distance should still, should also -1. Similarly, like the r minus dr and c minus dc. Actually, this is the entire code. I'm not sure if there's any typo or mistake, but let's just check. Yeah, as you can see, it works. Now let me submit it to check if it can pass all the testing cases. Yeah, as you can see, it passed all the testing cases and it's pretty fast. It's more than 90%. Now let's analyze the time complexity. So for this time complexity, basically we're gonna analyze we're gonna basically analyze like a basic Dijkstra's algorithm, but it is in a 2D array, and mn is just 100. So mn is just 100. So here, for the priority queue, and how many nodes will be inside the inside the priority queue. Yeah, let me check. So yeah, it will be mn. So there will be m times n node in total. In total, it will be put inside the priority queue. So it would be m times n times log m times n. So it is basically n squared, because m equals to n squared times log n. I think this is for the time complexity. Because for this PQ, while you use a heap push or heap pop, the time complexity will be log n squared. It is also similar to log n. Yeah, and we also need to check how many edges. Yeah, and while checking how many edges for each of the position, it's gonna have 4 directions. So it's gonna be it's gonna be 4 times m times n. So this is why it is n squared times log n, I believe. Thank you for watching. See you next time.